Okay, if angular acceleration is constant, then if we define angular acceleration to be the rate of change of angular velocity and angular velocity to be the rate of change of angular position, it follows that the change in angular velocity is the integral between two values of your clock time of the angular velocity with respect to t. And that is a direct consequence of angular velocity being the rate of change or the derivative of your, it's a direct consequence of angular acceleration. Let's start. Okay, now we recall that angular acceleration, represented by alpha, is the rate of change of angular velocity, represented by omega. And that omega, the angular velocity, is the rate of change of angular position theta. So that to find the change in angular velocity, we can integrate between two values of the clock time, the angular acceleration, and we find that the change in angular velocity is angular acceleration multiplied by delta t, provided again angular acceleration is constant. Or, more generally, our function omega of t, the angular velocity is a function of t, has a derivative equal to the angular acceleration, so the angular velocity will be an antiderivative of the angular acceleration with respect to t, and that means that omega of t is going to be alpha of t plus an integration constant, and that integration constant is easily shown to be the angular velocity omega at t equals 0. Then, change in angular position, since angular velocity is a derivative of angular position, we can integrate that angular velocity with respect to t, and the definite integral gives us, well, here's the integral for omega of t. We integrate that, we get this, and that integral between t1 and t2 would be this evaluated between t1 and t2. I've got equals, etc. here, but I'm going to pause a second and write in that expression. Now, the expression might or might not be useful, but we're just evaluating this between t equals t1 and t equals t2. Looks like I've got t2 written there. I should have t1. But what we get then is 1/2 alpha times the change in t squared. That would be change in t squared is tf squared minus t naught squared, because t goes from t naught to tf, so the t squared will go from t naught squared to tf squared. And this is to be distinguished from delta t quantity squared, which would be the delta t being tf minus t naught squared. And this squared is not equal to this squared unless t naught happens to be 0. T naught or tf happens to be 0. Now, more generally, theta of t is the integral of your omega function with respect to t. Your omega function, provided alpha is constant, is this. So we integrate this with respect to t, and I haven't written out all the details, but the antiderivative is clearly 1/2 alpha t squared over 2 plus omega of 0 t plus an integration constant, which we identify as theta naught, but I should really call that theta of 0. Theta naught does not necessarily mean theta of 0, so call that theta of 0. Now, these integrations are completely analogous to the integrations we would do for linear motion, where acceleration a is constant, and instead of omegas we're using v's, and instead of thetas we're using s or x as our position function. And the equations that we get are identical in form to the equations that we get for uniformly accelerated motion, with those correspondences between the alphas and a's, omegas and v's, thetas and x's or s's. I'll comment also that we have a very similar process. We just integrate the acceleration function to get the velocity function, angular velocity function. Then we integrate the angular velocity function to get the angular position function. But the details are going to be different if your acceleration function is a function of t that's not constant. We would still integrate it, assuming it's something we can integrate, and then we'd integrate that result, but it wouldn't look like this.